Let's say we have a two body having a position vector r and its coordinate is given by x, y, and z. If it has a mass m1 and m2 of each body, then the reduced mass mu is given by m1 m2 divided by m1 plus m2. If this system has a Schrodinger equation given by minus h cross square by 2 mu del square plus v of r, wave function psi of r is equals to e psi of r. This Schrodinger equation is time independent, meaning this equation is depending on the position vector r only. This part is called Hamiltonian h. This is operating on the wave function psi of r, which gives an energy eigenvalue E and a eigenfunction psi of r. We use this Schrodinger equation to seek the solution in terms of a single variable. Let's say we have a potential V of r. In this case, let's say V of r is equals to V1 of x plus V2 of y plus V3 of z. Then Hamiltonian also we can write hx plus hy plus hz, where hx is equals to minus h cross square by 2 mu t square by tx square plus v1 of x, and hy is equals to minus h cross square 2 mu t square by ty square plus v2 of y. Then similarly we'll write hz is equals to minus h cross square by 2 mu t square by dz square plus p3 of z. We know Hamiltonian h is equals to hx plus hy plus hz. Substituting the value of hx plus hy plus hz in the Schrodinger equation, we'll get the equation somewhat like this. We seek solutions which are products of three functions, each of single variable. That is, psi is a function of r, then the solution is product of three functions, that is x of x, y of y, and z of z. This is x. So x is a variable of x only, y is a variable of y only, z is a variable of z only. Substituting this in above equation and dividing throughout the equation by the same three functions, then the above equation after simple simplification takes this form. Here on the left hand side we have addition of three terms, on the right hand side we have constant, that is energy eigenvalue. If we observe the three terms on the left hand side of the equation, each term depends on one variable. Hence each of these term must itself be equal to some constant. If the first term is equal to constant Ex, and second term is equal to constant Ey, and third term is equal to constant Ez, then addition of these three constants must be equal to E. We may also write each term as independent functions, and the functions is given by minus h cross square by 2 mu t square by dx square plus v1 of x, and the function x depending on x is equals to ex x of x, and the second function minus h cross square by 2 mu t square by dy square plus p2 of y, function y of y is equals to ey y of y, and the third function minus h cross square by 2 mu t square by dz square plus v3 of z, z of z is equals to ez z of z. By separation of variables, we just now transformed the original partial differential equation into ordinary differential equations, which are easier to solve. By solving these ordinary differential equations and applying boundary conditions, we can find the wave functions and energy eigenvalues for different physical systems. We will next use this for solving problems like the infinite potential well, harmonic oscillator, and hydrogen atom.